Hello, in this video I will present you the soil transport module within GRASS GIS. Again, similar to the groundwater flow module, the solid transport model is purely operating on raster maps. So I will not show you in detail how to set up those raster maps because I've made so many videos now to show what the commands are to generate these raster maps. But I will talk you through what kind of raster maps you need and how I set those up. So for the solid transport, so for the advective part, we need an groundwater flow module in the background. So here I will simply use one of those examples I've used a lot in the other videos, having a simply groundwater flow from left to right, 1 meter hydraulic gradient over a 2000 meter length from left to right. So I will need this pressure head distribution right here. I do not need the status raster map. We will set up a slightly different raster map for the groundwater flow module. I will talk about that in a second. Just as a reminder here for you, we had directly boundary conditions on left and right to establish the hydraulic gradient from left to right. Due to bug, so there is an error in the current soil transport flow module, we will need the Q, so the source term, but I haven't used any in this simulation, so we will simply take the null raster map as a value for that. Right, and then we need porosity and we need hydraulic conductivity. Just to check you here, they all have are homogeneous of some decent value. We need the bottom of our aquifer, which was just as defined as our zero level, and we had the top unconfined layer of, I believe, 100 meter, also everything homogeneous. So those are all the raster maps you already know. And now we are coming to the raster maps you need to generate newly for the groundwater for the solid transport model. So what you additionally need is the raster map for the initial concentration. And here I simply started with providing some kind of concentration in the middle on the left domain, the left side of the domain, not directly on the boundary, a bit further in, so that now we have something that can be transported to the right with the stream and might be even diffusing a bit upstream. We need a raster map for internal sources, which we will not use in this example. So we will just use the null map here. I uploaded something from another old example of mine, just to give you a list of all the parameters you need, but we will just simply use the null vector for that. We need to provide diffusivity values. And here you see I took homogeneous distribution of a value of 0.00001, right, for the diffusivity. We also need to define a retardation vector. I put that one simply to 1. So we will not have here any retardation effects. And now that's interesting point. We come to the boundary conditions here, and you will see it looks different to the status map. However, the values changed a bit. So you will see here that we have a 3 on the left and right, which is defined, if you follow the man page, as transient boundary conditions, but bridge just means just Neumann boundary conditions, so the tracer can flow out to both of those boundaries, and we have no flow boundary conditions on the left and right. So very much similar to the flow module, just we do not have directly boundary conditions on left and right, but these transient boundary conditions on left and right. And this is already it. So now we can go to the groundwater flow module, go for selecting the solid transport model. Of course, again, you can do this using the command line. Again, I recommend using the command line, but I will here, for simplicity, do it by the graphical user interface. It provides us with all the things all the raster maps we need to provide. You see, that's quite a lot. So we need the initial concentration, we need the piezometric hat, which will be, as I said, the result from our groundwater flow module. We need the hydraulic conductivity, which is required here, so it can compute the velocities, right? So we need the status map here. We need the diffusivity tensor, the inner concentration, which I will not have, so I have set it to 0. I have the retardation factor, we have our effective porosity, we have our top layer, we have our bottom, which is just a null, and we can provide a list. And then the raster map, where it can provide us with the results, so with the final concentration distribution. And I go here for the ST result. I just named it that. You can provide it with any name you like. So, as you said, there is a bug, so the whole program doesn't work if you do not provide inner groundwater sources or sinks. But we can set it to null, so it doesn't matter. It just needs to be there, otherwise you're running into errors. For the solver, we do not need to specify so much here. I'm just increasing the number of seconds to be simulated so that there is actually happening. I will use flag for it to use the current fractal Levy criteria for time step calculations. So besides me providing a larger time step, the program itself will apply the CFL criteria, so it will compute what kind of time step is required to fulfill the CFL criteria, and it will split the time step I'm providing into as many time steps necessary of the size still fulfilling the CFL criteria. It does that to improve accuracy, which is a very neat thing. So if you remember, for the groundwater flow module, we had to track a lot of those parameters to come up with reasonable numbers. We don't do it here, but we set the flag for the CFI criteria. Also, not messing around with the flow-by-flow stabilization scheme, that is regarding the advection. Just keep it to full, and just trying to get a run on the first simulation. Here, we're just allowed to override results, as I do usually, and you can define a dispersivity value. I would just provide something like this, but of course you can, come up here. I mean, this is a reasonable number, but you can specify it, and it allows even anisotropy, right, with longitudinal transversal dispersivity. So this is already it, and we can hit the run button. You will see now here it goes several time steps. So the one time step I provided it's split up in 46 time steps to come up with the amount of time I wanted it to simulate, and provides us with some diffusive results. So if you see, that was my initial setup, and you see, because it was just an initial concentration, so of course it is vanishing here, and the whole concentration has been transported to the right. You see there has been some diffusive effects, also transversal, which is completely to be expected. There is quite a smearing from left to right, and now we can start analyzing that. So first of all, let's look at the legend. This is correct, right? So it says -0. Okay, so there might be some very minor minus values. So the units here, just remember it's written in the manual as well as in the graphical user interface as kilogram per cubic meter. I started with I believe 500 cubic meters. Kilograms per cubic meter. So this, of course, has been declined as it's spreading across. And as this is a very, very simple method or simple model, very much a 1D model, we can also profile it to get an idea about it. So let's just get a line across like that. Right, and this is the very nice bell-shaped curve, as you would expect it, with a little bit of a tail down here, which is to be expected due to the advective problem. It's not purely diffusive. It also has this advective component, so it's merging to the right, but you also see there has been quite heavily diffusive aspects because we pretty much started with a simple peak signal up here. So, there's numerical diffusion things. So now you could start analyze those kind of effects by, for example, setting the groundwater flow velocity to 0. So putting the pressure head value simply to 0 with no gradient and see what the diffusive effects then would be, or other way around, setting the hydraulic, not the hydraulic, but the diffusivity of the solute transport to 0 and see how much numerical diffusion you have if there is only advection taking place. Or things like this, we could also add another profile, just going vertical to it, right? And we see this is a very narrow diffusive frontier. So there's like 1, 2, 3, 4 grid points involved. Right, or visually we can only detect 3, maybe a bit on the 4. I'm not sure if you can see it in the videos. There's slightly bit variation, but now we have because it's such a simple 1D, well, pretty much a 1D problem, right? You could now analyze and see what is transport velocity. You could use statistical momentum analysis, of course, not on the transect, but on the longitudinal profile in flow direction, and do that kind of analysis. So this is already, so play around with the tool, getting used to it, and thank you very much for your attention.